Welcome. Today we're diving into the fascinating world of integration in mathematics. Integration is a fundamental concept that plays a crucial role in calculus and beyond. Whether you're a student just starting out or someone looking to refresh your knowledge, understanding integration opens doors to solving complex problems in physics, engineering, and economics. In this video, we'll break down what integration means, why it's important, and how it connects to other mathematical ideas. Let's begin our journey by exploring the very basics of integration and see how it fits into the bigger picture of mathematics. Integration at its core is the process of finding the whole from its parts. In mathematics, it's the reverse operation of differentiation. While differentiation breaks things down to their rates of change, integration helps us piece them back together to find total values, such as area, volume, or accumulated quantities. Imagine you have a curve on a graph. Integration allows you to calculate the area under that curve, which can represent anything from distance traveled to total profit. This powerful tool is essential for analyzing continuous change and accumulation in various fields. Concept of integration has deep historical roots. Ancient mathematicians such as Archimedes used early forms of integration to calculate areas and volumes long before calculus was formally developed. Over centuries, mathematicians refined these ideas, leading to the formalization of integration by Isaac Newton and Gottfried Wilhelm Leibniz in the 17th century. Their work laid the foundation for modern calculus, connecting integration and differentiation as inverse processes. This historical journey highlights the enduring importance of integration in mathematical thought. One of the most common applications of integration is finding the area under a curve. Imagine plotting a function on a graph. The area beneath this curve between 2 points can be determined using integration. This concept is especially useful in physics, where it can represent quantities like distance traveled over time when given a velocity function. By summing up infinitely small slices under the curve, integration provides an exact value for the total area, making it a powerful analytical tool. Integration comes in two main forms: definite and indefinite integrals. A definite integral calculates the exact area under a curve between two specific points, giving a numerical value. An indefinite integral, on the other hand, represents a family of functions and includes a constant of integration. Understanding the difference between these two types is essential for applying integration to real-world problems, as each serves a unique purpose in mathematical analysis. Integral symbol integral is a key part of integration notation. Introduced by Leibniz, it resembles an elongated to represent sum, reflecting the idea of summing infinitely many small quantities. When you see the symbol in mathematics, it signals the process of integration is taking place. Alongside the symbol, you'll often see limits of integration for definite integrals or a function, and a differential for indefinite integrals. This notation is universal in calculus and essential for clear mathematical communication. Integrate a function, you essentially reverse the process of differentiation. If you know the derivative of a function, integration helps you find the original function. This process involves identifying an antiderivative, a function whose derivative gives you the original function. For example, integrating 2x gives you squared, since the derivative of x squared is 2x. This reversal is at the heart of many calculus problems and applications. Antiderivative is a function that, when differentiated, returns the original function you started with. For instance, if you differentiate x cubed, you get 3x squared. So the antiderivative of 3x squared is x cubed plus a constant. This constant, often called c, is important because many different functions can have the same derivative, differing only by a constant. Understanding antiderivatives is key to mastering indefinite integrals. Whenever you perform indefinite integration, you add a constant of integration, usually denoted as c. This is because differentiating a constant gives 0, so any constant could have been present in the original function. Including this constant ensures that all possible solutions are captured. It's a small detail, but it's crucial for solving equations and understanding the full set of antiderivatives. Integration isn't just about numbers and symbols, it has a powerful geometric meaning. When you integrate a function, you're often finding the area under its curve on a graph. This area can represent physical quantities like distance, work, or probability depending on the context. Visualizing integration as area helps make the concept more concrete and connects it to real-world applications. Physics, integration is used to calculate quantities that accumulate over time or space. For example, if you know the velocity of an object at every moment, integrating that velocity function gives you the total distance traveled. Similarly, integrating a force function can give you the work done by that force. These applications show how integration turns mathematical ideas into practical tools for understanding the physical world. Economists use integration to analyze accumulated quantities, such as total profit, cost, or revenue over time. By integrating a rate function like marginal cost or marginal revenue, you can find the total cost or revenue. This approach helps businesses and policymakers make informed decisions based on continuous data, demonstrating the versatility of integration beyond pure mathematics. Engineers rely on integration to solve problems involving accumulation, such as determining the total load on a structure or the amount of material needed for construction. By integrating functions that describe changing quantities, engineers can design safer and more efficient systems. This practical use of integration highlights its importance in building the world around us. Probability and statistics, integration is used to find probabilities and expected values for continuous random variables. By integrating a probability density function over a certain interval, you can determine the likelihood of different outcomes. This application is essential for analyzing data and making predictions in fields ranging from science to finance. Fundamental theorem of calculus links integration and differentiation, showing they are inverse operations. It states that if you integrate a function and then differentiate the result, you return to the original function. This powerful connection allows us to solve a wide range of problems and is a cornerstone of calculus. Before we can perform integration, we often approximate the area under a curve using Riemann sums. This method involves dividing the area into small rectangles, calculating their areas and summing them up. As the rectangles get narrower, the approximation becomes more accurate. Riemann sums provide the foundation for understanding definite integrals and the concept of limits. The concept of limits is central to integration. As we make the slices under a curve infinitely thin, the sum of their areas approaches the exact value of the integral. This process relies on the mathematical idea of a limit, which allows us to handle infinite processes in a precise way. Understanding limits is key to grasping how integration works at a deeper level. Definite integrals use special notation to indicate the interval over which you're integrating. You'll see the integral symbol with lower and upper limits written at the bottom and top. This tells you exactly which part of the curve you're finding the area for. The result is a specific number, representing the total accumulation between those 2 points. Integrals have several important properties that make them useful in calculations. For example, integration is linear, meaning you can split up the integral of a sum into the sum of integrals. You can also factor out constants and combine intervals. These properties simplify complex problems and make integration a flexible mathematical tool. Some functions appear frequently in integration problems, such as polynomials, exponentials, and trigonometric functions. Knowing how to integrate these basic functions is essential for tackling more complex problems. Each type of function has its own integration rules, which you'll encounter often in calculus. Integration by substitution is a technique used to simplify complex integrals. By changing variables, you can transform a difficult integral into one that's easier to solve. This method is especially useful when dealing with composite functions and is a staple in calculus problem solving. Integration by parts is another powerful technique, based on the product rule for differentiation. It allows you to break down the integral of a product of functions into simpler parts. This method is particularly useful for integrating products of algebraic and transcendental functions, expanding your toolkit for solving challenging integrals. When integrating rational functions, breaking them into partial fractions can make the process much easier. By expressing a complicated fraction as a sum of simpler ones, you can integrate each part separately. This technique is especially helpful for functions with polynomial numerators and denominators. Improper integrals deal with infinite limits or unbounded functions. These integrals require special techniques, as the area under the curve may extend infinitely or the function may have discontinuities. By carefully applying limits, mathematicians can determine whether these integrals converge to a finite value or diverge. Sometimes, it's impossible or impractical to find an exact integral using algebraic methods. In these cases, numerical integration techniques such as the trapezoidal rule or Simpson's rule provide approximate answers. These methods are widely used in science and engineering when dealing with complex or real-world data. Integration isn't limited to single-variable functions. In higher mathematics, you'll encounter double and triple integrals which calculate volumes and other quantities in multiple dimensions. These advanced techniques are essential for fields like physics, engineering, and probability, where problems often involve more than one variable. Integration isn't just an abstract concept, it has countless real-life applications. From calculating the area of irregular shapes to determining the total amount of resources needed for a project, integration helps solve practical problems. Its versatility makes it a valuable tool in science, engineering, economics, and everyday life. Many physical and engineering systems are described by differential equations. Integration is a key step in solving these equations, allowing us to find functions that describe how systems evolve over time. This connection makes integration essential for modeling and predicting complex behaviors in science and technology. Sometimes, you need to find the area between two curves rather than just under one. Integration allows you to calculate this by subtracting the area under the lower curve from the area under the upper curve. This technique is useful in many applications from economics to engineering. Integration can also be used to find volumes of solids, especially those with irregular shapes. By rotating a curve around an axis and integrating, you can calculate the volume of the resulting solid. This method, known as the disk or shell method, is widely used in engineering and design. Finding the center of mass of an object with varying density requires integration. By integrating the density function over the object's shape, you can determine the balance point. This application is crucial in physics and engineering, especially for designing stable structures and vehicles. Probability density functions describe the likelihood of outcomes for continuous variables. Integrating these functions over an interval gives the probability of outcomes within that range. This concept is fundamental in statistics and data analysis, helping us make sense of uncertainty and variation. In physics, the work done by a variable force is found by integrating the force function over the distance moved. This allows us to calculate the total energy transferred, even when the force changes along the path. Integration makes it possible to analyze complex systems where forces aren't constant. Biologists use integration to model population growth, the spread of diseases, and the accumulation of substances in organisms. By integrating rate functions, scientists can predict future trends and understand how biological systems change over time. This demonstrates the broad impact of integration across scientific disciplines. At its heart, integration is about accumulation, adding up infinitely many small contributions to find a total. Whether it's distance, area, volume, or probability, integration provides a systematic way to handle continuous accumulation. This perspective helps unify the many different applications of integration. Modern technology relies heavily on integration, from computer graphics to signal processing. Calculating areas, volumes, and accumulated values is essential for rendering images, analyzing data, and designing electronic circuits. Integration bridges the gap between abstract mathematics and practical technology. You might not realize it, but integration appears in everyday life. Calculating the total amount of water used, the distance driven, or the energy consumed all involve integrating rates over time. This shows how mathematical concepts like integration are woven into the fabric of daily activities. Optimization problems often require integration to find maximum or minimum values of accumulated quantities. For example, maximizing profit or minimizing cost over time involves integrating rate functions and analyzing the results. This application is vital in economics, engineering, and management. In computer science, integration is used in algorithms for graphics, machine learning, and data analysis. Calculating areas, probabilities, and accumulated values is essential for building intelligent systems and processing large datasets. Integration helps computers make sense of continuous information. Signal processing relies on integration to analyze and manipulate signals such as sound or images. By integrating signals over time or space, engineers can filter noise, extract information, and improve communication systems. This application is crucial for modern technology, from smartphones to medical devices. Environmental scientists use integration to model the accumulation of pollutants, the flow of water, and changes in ecosystems. By integrating rate functions, they can predict future conditions and assess the impact of human activities. This helps guide policy and protect natural resources. In medicine, integration is used to analyze the spread of diseases, the effect of drugs over time, and the accumulation of substances in the body. By integrating rate functions, healthcare professionals can make better decisions about treatment and prevention, improving patient outcomes. Astronomers use integration to calculate distances, masses, and the motion of celestial bodies. By integrating functions that describe gravitational forces or light intensity, they can unlock the secrets of the universe. This shows how integration helps us explore the cosmos and expand our understanding of space. Even in art, integration plays a role. Artists and designers use mathematical integration to create smooth curves, calculate areas for materials, and design visually pleasing compositions. This blend of math and creativity demonstrates the universal appeal and utility of integration. Wrap up: integration is a cornerstone of mathematics with far-reaching applications. From calculating areas and volumes to solving real-world problems in science, engineering, and beyond, integration helps us understand and shape the world. By mastering this concept, you gain a powerful tool for analysis, problem-solving, and innovation. Keep exploring, and you'll discover even more ways integration enriches our lives and advances human knowledge.